Let us study how to represent a complex number by what is called as Argand diagram. So, as we are familiar with the xy coordinate frame of axis, so we have the x-axis and the y-axis, and if we want to denote some number, say 3, 2, what do is we mark off the distance at 3 on the positive x-axis, and on the positive y-axis also we mark off the distance 2, and that is where we get the point 3, 2, and we call 3 and 2 as the x and y coordinates of that point. So we use the same analogy even to plot the complex number on what is called as a complex plane. Now the only difference in the terminology is that for the real numbers we need to have only one real number of line, but since we have now the complex number which consists of real as well as imaginary part, what do is we still take a pair of perpendicular axes, but we don't call them as x and y, but we call them as real axis and imaginary axis. So we plot the real part on real axis and imaginary part on imaginary axis. Let's consider some number, something like in general a plus bi as the complex number to be plotted on the complex plane. So what do is we take a, which is the real part on real axis, and this is b, which is the imaginary part on imaginary axis. So therefore at the intersection we have this particular number z, nothing but a plus bi. So that's the way we represent complex number on Argand diagram. Now let's move ahead and study some of the very important parameters related with a complex number. In that, first we have the conjugate of a complex number. Now suppose we have a complex number z denoted in general as a plus bi, as we know, where a and b both are real numbers. The conjugate of this complex number is denoted by z bar, and it is obtained by changing the sign of the imaginary part only of the original complex number. So now here we see the imaginary part is b. So what we have to do is we have to just change the sign of this imaginary part. So therefore the conjugate of z is nothing but a minus bi. So this is what is the conjugate of a complex number. Just to see the graphical meaning of this, suppose we have a complex number, say z is equal to 3 plus I. So that means we have 3 units on the real axis and we have 1 unit on the imaginary axis. So therefore this particular number is the original number z is equal to 3 plus I. Now if we want to take the conjugate z bar, what do is we change the sign of imaginary part and hence we get 3 minus I. So when we say 3 minus I, it's nothing but the real part is 3 and the imaginary part is minus 1. So therefore to take the minus 1 we must go on the negative side of the imaginary axis. So the distance is still 1, but since the direction is opposite, it is actually minus 1 as the imaginary part. So therefore this is where we have z bar as 3 minus I. So if you see, the conjugate of a complex number is nothing but mere reflection of any complex number in the real axis. So that is the geometrical interpretation of conjugate of a complex number. Now let's move ahead. Now we define two additional important parameters of a complex number. In that the first one is modulus and second is argument. Now let's once again see the representation of a complex number on Argand plane. Let z be a complex number equal to a plus bi. So we know that the distance on the real axis here is a, whereas the distance on imaginary axis is b. And here we have the origin, which is nothing but the number 0, because the number 0 has real as well as imaginary parts both as 0. Now the modulus of the complex number z is nothing but defined as the distance of that number from the origin. So if we join the 2 points, we get the modulus of z like this. Now as we know, the triangle shown here is a right angle triangle, and hence by Pythagoras theorem it is clear that the square of hypotenuse is nothing but the a square plus b square. So in other words, the modulus, which is nothing but the hypotenuse of this triangle, turns out to be square root of a square plus b square. Many times this is also denoted by r, which is same as the modulus of the complex number. Now further we study the argument, or also called as the amplitude of the complex number. This is denoted as arg of z or amp of z. Now what is the argument? Now here if we consider the angle which is made by the segment joining origin and the complex number as measured from the positive real axis in anticlockwise manner. So this particular angle is called as the argument of the complex number. So argument is defined as we can see in the triangle, it is clear that the relation between the theta, b and a is nothing but that of tan of theta, because these three are connected by the tan relation. And as we know that tan theta is equal to b upon a, which is opposite upon hypotenuse, the argument of z, which is nothing but theta, is nothing but tan inverse of b upon a. But here we have to keep in mind that we have to consider the correct quadrant before we evaluate the value of tan inverse. So therefore it is absolutely important that we take the correct angle pertaining to a and b. So if a and b both are positive, it means the complex number is in first quadrant. So we will get the argument as some angle which is between 0 and 90 degrees and so on. So if a and b both are negative, the angle will be from the third quadrant and so on. Now technically this particular argument is also denoted as theta, that theta has to lie between minus pi and pi. So it is something like we can go from 0 to pi or 0 to minus pi, because taking anti-clockwise is positive and taking clockwise is negative. So this is where we can have the range of argument.